Okay, so in this lab, we're going to use a force sensor to actually pull a cart with varying amounts of mass inside of it. So I zeroed it out there. There's our force sensor. Here's our wonderful cart. I'm going to add 1 kilogram. We should probably know how much the cart weighs first because we're going to need the information. So there's listed to 20.6 grams. Okay, hooking up the force sensor to the cart here with the 1 kilogram inside plus the 220. We're going to go ahead and pull this, and we'll think about what the opposing force here is in a second. But right now, I just want to see, okay, if I hit play, can I get a generalized reading on the force on this cart over time? Now I'm going to pull it so I have a constant velocity. And as I do that, I'm going to go ahead and get a reading that looks something like this. Looking closer, we can see that actual force is 2.358 newtons. Okay, so as always, the smartest thing here would probably be start with a free body diagram. So I've got my generalized cart sitting in place here. I got the various masses inside. I know this is a great drawing. I love this. So there's our masses. And if we think about it, of course, we have the force of gravity working directly down. I have this applied force that's kind of pulling this direction. And then we're going to think about, okay, well, what is opposing that force? Well, first of all, besides the force of gravity, we should also have a force normal pushing this direction. Oh, nice straight line. You're going to love that. So here's our force normal kind of acting opposite gravity. And then, of course, if we're at a constant velocity, we should have essentially for this whole idea, our net force should be 0 in both the vertical and horizontal. So with this force applied, it's kind of moving this direction, or if you want to think about it as a tension, it's fine. We're not really attached to a string, so I'm just going to say it's applied on this pole. Of course, most of you will realize we have something opposing it that's equal, the force of friction. So if I think about the fact that I'm at a constant velocity or a net force of 0 in my horizontal direction, I could say the force applied minus the force of friction should be equal to 0 since I have a net force of 0 or constant velocity. Therefore, the force applied that I'm actually measuring with my force probe is my force of friction, just working in different directions. So every time we take our data set, we're actually looking at this, but in reality, it's showing us our force of friction. So the question is, how does the force of friction actually change as we start adding different masses to it? Okay, so in this case, I'm going to add 500 more grams to it, so a half kilogram. So I've got a total of 1,500 inside our cart, which also weighs 200. And now we're going to go ahead and do the same thing. Now it's important to have a constant velocity here, otherwise the object's going to be accelerating and we can't make the assumption the force of friction is equal to that force applied. Go ahead and pull with an additional 500 grams inside of there. And as expected, we get some data set that looks very similar. In this case, though, we can see the actual measurement on our force, though, is 3.3 newtons as compared to what we originally had in that first trial. So on the side-by-side here, you can see both trials. Initially, we have a 1 kilogram mass of 2.358, and on the other side, we have a 1,500 kilogram mass plus the additional cart value. And of course, we can see a higher value. Something else I want you to notice, though, is that in both of these situations, we actually have a peak that starts before it even begins. And you can consider that the force applied that starts or sort of activates the entire thing into a motion. And if we think about what we know about friction, there is static friction, or the friction, that we have to overcome to actually start motion. And then we have kinetic friction, the friction that's actually applied while the object is moving. That peak, which I'll show side by side here, is again representative of what we're actually looking for in the difference between what's called the force static or force friction static in the cart initially, and then as we change the mass as well. Net force of 0 are balanced here. Our force normal and force gravity cancel out in the vertical, and our force applied and our force friction are equivalent because we have a constant velocity or no acceleration. So the question becomes, if we start looking at this force of friction, what happens to it as we start changing the mass? And I think most of you will see from the data that the force required to move it is going to be more. So overcoming that friction and actually getting that motion going is going to be more, and then keeping it in motion is going to require more force as we continue to add mass. So with that in mind, the question sort of becomes why, and which force are we actually changing, and is it actually something we can sort of graph out? I've got the total mass of the cart, 220.6. I've got the added masses for each one of my trials. I only did, 7 trials here. What was that, 6? Yes, 6 trials. Sorry, I lied. And what the force friction kinetic represent is that stabilizing force, as we saw in the graph in the first section of the video. The force friction static would indicate that upper peak right before we hit that little flat line. Now, in order to analyze this, I'm going to have to look at forces, not just at mass, because we were in a free body diagram situation. So I'm going to sort of insert a couple things in here. And if I go ahead and insert a column, let's go to the left. I want to have a column for my total mass, and I really would like to have this in kilograms, not sitting in grams. So if I do that, I would take, A3 plus the 220.6, but if I need that to actually be divided by 1,000, so I can actually have this set up into kilograms rather than grams. Do that. Do I want to do it for everything? Yeah, I sure do. Okay, now I've got total mass, and if I was going to keep that in mind, thinking about my free body diagram, the mass times gravity would indicate our force gravity. So let's go ahead and insert another column to the right. Let's call this force gravity. And this, of course, will be in newtons, so I'm going to mark that as well. So that would be our mass times 9.8. And we can do 9.81. Let's just go 9.8. Do I want to autofill? I sure do. All right, so now I've got my force gravity and I got my force friction. Huh, that doesn't seem to be helping me so much. So at this point, you kind of want to almost cheat off your AP1 equation sheet. And spoiler alert, you kind of already know this equation. We know that the force of friction is going to be highly dependent on the surface. Well, the surface force is force normal. So if that's the case, it's not so much that we want the force of gravity, we actually need to know the force normal. Luckily for us, we did this on a horizontal, so those two should be equivalents. So when I write force gravity here, we could also just say, let's insert one more column to the right, and our force normal, which would be newtons, would of course be all of these values into the exact same spot. Now, if you try and copy and paste it over, it might get a little bit messy. So I'm going to go ahead and scrub down and let's paste. Yeah, look what happened. It pulled C4, C3, and all this stuff times 9.8. I don't want to do that. So Control Z that thing, and we'll just kind of go across and look at it. The question, though, is we are changing what? Well, mass, but what force are we actually changing? I would argue you're changing your force normal. You're changing how much force is actually on that particular object. And we're keeping this surface constant. We were measuring it across kind of that cardboard, I don't know, ramp, for lack of a better word. And we're seeing what happens to our force friction kinetic. So what I really want you to look at is try and graph our force normal versus, our force friction kinetic and see what happens. And you could also do the same thing for force friction static. What would the slope actually represent? And that's kind of what we're going to be talking about as we get into this tomorrow.